Hello, dear students. Welcome you all. Students, in today's lecture, we are going to discuss what a what low pass filter of second order, right? Filter, and it is of a second order, right? We have discussed the Butterworth low pass filter of first order in the early lecture, and we have derived the expression for the frequency response. Now we are going for the second order, right? So in second order, obviously there will be two filtering sections or filtering units, right? Instead of one filtering unit, right? This is the difference between whatever low pass filter of first order and second order, right? So first of all, we will draw the circuit diagram for this second order filter, right? So for it, we will take a operational amplifier. This is operational amplifier. Right. So here we will have one resistor there, one section, second section, and right. This is for the input signal that is applied from here, right? This is for plus BCC and minus BEE, right? So now I can draw the resistances here. This is R1. This is RF, feedback resistance, right? Uh, R2. This is R3. This is R2. This is virtual ground, right? This is negative, this is positive. It means this is non-inverting terminal, this is inverting terminal, plus VCC minus VEE. Clear? This is for V out. Clear? Now we will also connect two capacitors. This is for the first section, and this is for the second section. We have two sections, right? This filter is connected with the output, right, through this capacitor, right? Now this is the space for providing input signal, B input, plus and minus. Clear? It is virtual ground. It is space for capacitor C2. This is C3. Clear? it is at the virtual ground, right? So this capacitor is connected with the output, right? This is right. Now we have to draw the load resistance also, across which we are going to take the output. This is load resistance. This is okay, right? This is A. F is the gain of this basic amplifier. Let this node is node 2 and the voltage at it is V2. This node is node 1 and the voltage at this node is V1. This node is node A and the voltage appearing at this node is voltage VA, right? Let's see at the different currents that is flowing in this circuit, right? Uh, let this current flowing toward this side is I1, clear? The current flowing toward this side is I2, because at this node some of the current will go toward this side, some of the current will go toward this side. Yes, this current is I3. Again at this node the current will get divided. Some current will go toward this side and some current will go toward this side. But we know from the theory of operational amplifiers that the input impedance of the operational amplifier is very high. So it means nearly zero current flow toward this side. It means same amount of current I3 is flowing toward this side. Clear? Now this is basically what, if I look at this circuit of the operational amplifier, it is operational amplifier working in the non-inverting mode, right? So B output, expression for B output is 1 plus RF upon R1 into B1. The voltage appearing at this node 1. Clear? This is the expression. This expression I have taken from the theory of operational amplifiers, right? So if I want to analyze this entire circuit, then first of all I have to find the value of B1, because then I will put the value of B1 here and I will find the expression for a B output, and from then I can found B output upon B input. Clear? This is what? This is a transform function for this particular circuit. This B output upon B input magnitude will tell us about the frequency response of this circuit, that how the different frequencies pass through this circuit, right? Different frequency, for which different frequencies? This input signal. Clear? So first of all we will drive the expression for V1, then we will proceed further and we will write down the expression for a transform function. Clear? Now I'm going to solve the this particular part of this circuit, right? Because I want to calculate the value of B1. Clear? So if I know the value of B1, then I can write the expression for a B output. Clear? Then I can proceed further for finding the frequency response or a transform function of this. Right? So this is what? This is the circuit diagram of Butterworth low pass filter of second order. You can see here we have two filtering sections. This one is the first filtering section. This one is the second filtering section. Two filtering sections are applied here. That's why we call it as a second order low pass filter. Right? Now, in order to simplify this part of the circuit, as I told you, I will draw a simplified diagram of this circuit. Right? use this for it. Right. Now this is R2, R3, C2, this is C3. C3 is at virtual ground, whereas this is connected with the B out. Clear? This is toward the base of the transistor of operational amplifier, and this is B input. Clear? Now this is the simplified diagram of this part of the circuit. Clear? Here this is node A, and the voltage at this node is VA. This is node 1, and the voltage at this node is V1. Clear? If I look at the different currents flowing in this circuit, then this is I1, this is I2, this is I3, and this is again I3. Clear? If I write down the value of the resistance, or in more uh, detailed form, I can say that that is reactance, right? Capacitive reactance. Then that will be 1 upon SC2. S is equal to iota vega. Clear? Vega is 2 pi F. So it will become capacitive reactance for this. Capacitive reactance means the opposition offered by this capacitor to the flow of current through it. Similarly, for it, it will be 1 upon SC3. Clear? So this term and this term basically represent the reactance, right? For this capacitor and this capacitor, we can say these are basically resistances, right? We know the difference between resistance and reactance, right? Generally, impedance Z of any material is expressed as R plus iota X. Here R is the resistance part and X is the reactance part. Resistance is a real quantity, but this is an imaginary quantity. Reactance, capacitive reactance, inductive reactance, right? And this is resistance, right? So all these things are basically opposition. Clear? So now I'm simplifying further this simplified form of the circuit, right? So to simplify it, I have to consider node A first of all, and write down the junction rule at node A. So applying junction rule. At node A. Clear? What is it? I1 is equal to I2 plus I3. Clear? You can see here at node A. So I1, if I write it in terms of voltage and resistance, then it will become B in minus BA upon R2 is equal to I2. I2 means BA minus B output upon 1 upon SC. We are looking at this. Clear? BA minus B output upon the resistance part, that is, and then plus I3. I3 means BA minus B1 upon R3. Let this is equation number 2. This was equation number 1. Now, in order to solve equation number 2, I require the value of BA. Clear? So, to find out the value of BA, we are now going to consider node 1. Node 1, and at this node, I am applying the junction rule. Clear? So, according to the junction rule, I3 must be equal to this current plus this current. But the current toward this side is nearly equal to 0. So, it means I3 is equal to I3. I3 is equal to I3 at node 1. Clear? So I3 is equal to I3 means I can say I3 means BA minus B1 upon R3 is equal to B1 upon 1 upon SC3. You can see B1 minus here it is 0 basically, so it is 0. So obviously it is B1, right? So now simplifying this expression for BA. Clear? I will get BA is equal to R3 C3 S. Clear? Plus 1 divided by B1. This is equation number 3. Clear? Now putting the value of BA from equation number 3 in equation number 2. Clear? Then after solving that, we will get the value of B1, because what we require? We require the value of B1 for putting in this expression, right? Here. So I'm going to put this VA here. I'm eliminating the value of BA from here after putting this here. Then I will solve it for B1. I will get B1 is equal to, after simplification, B1 is equal to R3 B in plus R3 R2 C2S into B output divided by R3 C3S plus 1 bracket R2 plus R3 plus R2 R3 C2S minus R2. Clear? So I got this equation number 4, when I put this term here and I simplified it for a B1. Clear? Now we know B output is equal to 1 plus RF upon R1 into B1, equation number 5. So now I'm going to put the value of B1 here and let this is equal to AF. We know it from the theory of operational amplifier. So B output is equal to AF into B1. Clear? So what it will be, B output will be we will multiply this term by AF. Clear? And then after we will solve it, right? So I will put the value AF here, and then this will give us B output. Clear? It will become B output is equal to this multiplied by AF. Clear? And this is equation number 6. Now we will rearrange this equation and simplify this equation for B output upon B input. Clear? We can do it. That will be AF. You can see it after simplifying this equation. AF upon S square plus R3 C3 plus R2C3, clear, plus R2C2 plus minus AF R2C2 clear into S divided by R2 R3 C2 C3, and here it is plus 1 upon R2 R3 C2 C3, clear. So we have simplified this equation. Now let this is equation number 7. We have simplified this and converted it to this form for B output upon B input, right? Now I can write this equation B output upon B input is equal to AF upon S square plus 2 zeta vega n S plus vega n square, clear. Here zeta is called damping factor, clear, that is equal to this factor, clear, and vega n is called natural frequency of this filter, and it is 1 upon R2 R3 C2 C3, clear, right? uh, Vega n square, it was vega n square is equal to this, sorry, and then vega n will obviously becomes 1 upon R2 R3 C2 C3 under the root, clear, plus minus, but we are ignoring the negative sign because frequency is always positive, right? Okay, actually it was vega h, so we have mistaken here, I have mistaken here, sorry for it. It was vega h, clear. Clear. So it was vega n, natural frequency that I have written here, and vega n, it was not square, it was a vega n is equal to this. So this was wrong. Vega n is equal to this. This is about the natural frequency, vega n, clear. And this is damping factor, and vega h, the highest frequency or cutoff frequency that can pass through this circuit, wh is equal to wh square, basically it is not wh, it is equal to 1 upon R2 R3 C2 C3 C2 C3, clear. So vega h is equal to 1 upon under root R2 R3 C2 C3, clear. So obviously FH will become 1 upon 2 pi under root R2 R3 C2 C3. So this is equation number 8. This is the maximum frequency that can pass through this circuit, clear. So this is cutoff frequency or highest frequency, clear. And this expression b output upon b input, this is the transform function. Clear? B output upon B input, that is equal to, once again I am writing it, AF upon S square plus 2 zeta vega N S plus vega H square. This is the expression for a transform function. Clear? Now if I put iota S is equal to iota vega. If I put S is equal to iota vega in this equation and then I took the magnitude of it, then we can see it will come out to be B output upon B input magnitude. Then it will be AF upon 1 plus F upon FH power 4 and whole term under the root. Okay, this is the frequency response of this. This equation tells us about the frequency response of this second order low pass filter, right? So what is the difference between the first order and second order? Clear? You can recall that expression of the first order and see the difference. This is equation number 9, right? I can recall that value. It was AF upon 1 plus F upon FH square under the root. This was the case of first order low pass filter. This is the case of second order low pass filter, B output upon B input. So when you will plot this function, clear, then you can see that we will get a frequency response of the same type, but in this case, this is the graph that we can plot between the gain and frequency of the different signals passing through this circuit. Then this is gain B output upon B input, and this is frequency F. See, this is F toward this side. So again, you will get this type of response. Right. So here, this is the highest frequency that is allowed to be passed from this filter, and this is FH. Clear? If we plot this side, clear, then we will get this type of this. Clear? When F is less than FH, right, then gain is nearly equal to AF. Clear? Gain is nearly equal to AF. But as F is equal to FH, so again you will put it here, sorry, in this equation, F is equal to FH. So again the same thing, it will become AF divided by under root 2. So at this point, you know, the gain will be slightly low. Clear? In actual, this graph will be, this is the ideal. This response is an ideal response, right? This response is basically the ideal response. Clear? Ideal. Clear? In reality, it will be like this. Clear? So at F is equal to FH, this is the value of the gain. But if F becomes greater than FH, then the gain will attenuate. It will reduce, right? And the roll off rate in this case will be minus 40 decibels per decade. Clear? Means the roll off rate, the attenuation rate is 2 times to the rate of first order filter. Clear? First order filter. So this is the frequency response of this second order low pass filter. Clear? In this, here it is the pass band and it is a stop band. Clear? Uh, in the stop band, right, the gain reduces and then ultimately it will become a zero. Clear? As the frequency keep on rising, right? So first of all, we have drawn the circuit diagram. This is the circuit diagram of Butterworth low pass filter of second order. Then we found the value of B1. Clear? By simplifying this entire circuit in this way, right? And then we write down the expression for B output by putting the value of B1 in this expression here. Clear? Then when we put the value of B output, B1 in this expression, then this becomes equation number 6. Then we rearranged it for V output upon B input. We got this equation. I write it in the simplified form. This equation is basically transform function. Here zeta is damping factor, vega n is the natural frequency of this circuit. 1 upon R2, R3, C2, C3. Vega h is the cutoff frequency, and this is defined as this. Clear? So fh is equal to this. Clear? So then after we put s is equal to iota vega here, and then we took the magnitude of this transform function, then it gives us this expression. Clear? Then I plot this expression for frequency versus gain, then I got this graph. So this graph is the frequency response of this circuit, and it tells us that in case of low pass filter of second order, the roll off rate is 2 times to the roll off rate of first order filter, right? So this is all about the Butterworth low pass filter of second order, right? So thank you very much.